Hello, today I would like to discuss calcium channel blockers and um, the objective of this lecture are listed here. So calcium channel blockers are drugs that basically can be used in the treatment of hypertension and many other conditions. And at the end of this lecture, I will expect you to understand the mechanism of action of calcium channel blockers, um, be able to recognize on an exam the chemical scaffold. That's a big word for be able to recognize the structure of this molecule. Um, if shown a particular structure, be able to recognize if this is a calcium channel blocker. Understand the role of specific functional groups and what role they play in pharmacokinetics and pharmacodynamic of the drugs. And finally, be able to predict how modifications to key positions on the pharmacophore can influence the activity of the molecules. So, as a brief introduction, calcium channel blockers are compounds that can block the inward movement of calcium through what we call slow cardiac channels. The specific type of cardiac channels here are the L-type calcium cardiac channels. So there's different ways, different names for calcium channel blockers. They can be called calcium entry blockers or calcium antagonists. Calcium entry blockers or calcium antagonists. Now, chemically speaking, calcium channel blockers can be divided in four broad classes with distinct pharmacological profiles. The four broad classes are listed here, and you have the 1,4-dihydropyridine. Nifedipine is one of the examples of this class of drugs. Oftentimes they're simply referred to as the dihydropyridines. Then you have the phenylalkylamines. Verapamil is part of that class, of phenylalkylamine. If you see, there is a phenyl group here. This is an alkyl chain, and then the amine is in this position. So phenylalkylamines. Then you have the benzodiazepines, and diltiazem is part of that class of medications. And finally, we have the diaminopropanol ethers. This class is included here for the sake of completion. Actually, bepiridil is not available on the US market. So the drugs that we're actually going to cover in this lecture are the dihydropyridines, the phenylalkylamines, and the benzodiazepines. Now, again, for the purpose of this lecture, I would like us to simplify these concepts. I would like us to simplify that into two groups. We're going to consider the dihydropyridines, all right, and everything else that's not a dihydropyridine, we're going to lump them into a big class called the non-dihydropyridines. So dihydropyridines and non-dihydropyridines. Let's look at the mechanism of action of these drugs. Calcium channel blockers bind to allosteric receptors. By that I mean they don't bind on the same. They don't bind at the same site as calcium. They don't bind at the same site where calcium will bind. So they bind at a different site. So this is different than calcium itself. And these allosteric receptors are located within the alpha 1 subunit of the L-type calcium channels. Okay, alpha 1 subunit of the L-type calcium channels. Now, a few interesting facts about the binding of of these molecules to the receptor, when verapamil binds to its receptor, it actually inhibits the binding of both diltiazem and of the dihydropyridines. So the binding of verapamil to its receptor prevents or inhibits the binding of the other types of calcium channel blockers from binding to their receptors. The binding of diltiazem or dihydropyridines to their receptors inhibit the binding of verapamil. So that means once diltiazem binds to its particular receptor, it causes a conformational change in the calcium channel to block the binding of verapamil. And the same for the dihydropyridines. Once the dihydropyridines bind to the receptor, there is a conformational change that occurs in that receptor that then prevents the binding of verapamil. Finally, the binding of diltiazem and the dihydropyridine mutually enhance each other. So there is a conformational change inside of that receptor after diltiazem binds that allows dihydropyridines to bind even tighter to the receptor. Now, the structure activity data that's available for this class of drugs is mainly available for dihydropyridines because verapamil and diltiazem are the only drugs in their individual classes. Okay, so they are the only drugs in their class. Only drugs in their class. All right, so let's take a quick look at the structure-activity relationship of the dihydropyridines. Now, this picture here that's taken from Fourier's principles in medicinal chemistry is a good summary of the structure-activity relationship of the dihydropyridines. Okay, so the first thing that's very important is you want to have a substituted phenyl ring at the C4 position. Okay, I guess let's number these different positions here for clarity's sake. So this will be position 1, this will be 2, 3, 4, so this will be 5, and this will be 6. So having a substituted phenyl ring at the C4 position here, this is the phenyl ring. Having a phenyl ring at this position here optimizes activity. Now, other heteroatomic rings, such as pyridine, have been observed to cause toxicity in animals, and so you will not see other heteroatomic rings at the 4 position. We are only going to stick with the phenyl ring at this position. Then the second important factor is that substitution of the para position decreases activity. Okay, so the para position of this benzene ring, if you substitute at this position, you end up with a decrease of the activity. So it's best to leave that para position totally unsubstituted. Best to leave it totally unsubstituted. However, any substitution at the ortho or the meta position is actually going to increase activity or produce optimal activity in the compound. So substitution at the ortho or meta position is going to increase activity. Now, the ortho-meta substituents help maintain the C4 aromatic ring in the position perpendicular to the dihydropyridine ring. So when you have a substitution at this position or that position, because of the bulk, because of the sterics that's involved in those groups that you substitute here, they will force this phenyl ring to orient itself in a perpendicular way to the dihydropyridine ring here. And that perpendicular orientation is essential for the activity of the dihydropyridines. Obviously, the 1,4-dihydropyridine ring itself is essential for activity, and any substitution at the N1 position, this position here, is actually going to abolish activity altogether. Now, when you look at these groups, these dihydropyridines, you notice that you have groups at the C3 and the C5 position. So having ester groups at these two positions, C3 and C5 position, enhance or optimize the activity. Now, if you put other electron withdrawing groups at those positions, they will actually decrease the antagonist activity. So electron withdrawing groups at this position will decrease the antagonist activity, or they will show agonist activity, meaning instead of blocking, they will actually start enhancing or activating the calcium channel. So you have to be careful when you do those substitutions. You want ester groups at those positions. Asymmetric compounds have more selectivity for specific blood vessels. Oftentimes, asymmetric compounds are compounds that have different substituents at the 3 and 5 position. 3 and 5 position. You have those asymmetric compounds. And so those compounds are usually more selective for specific blood vessels, and they're the ones that are preferentially developed. There's one last point here to make on the structure-activity relationship before we talk about the physical chemical properties of these drugs. It is possible to have substituents larger than methyl at the C2 and C6 position. Okay, it's possible. So in the case of nifedipine, you have two methyls. You have one here at the C2 position, and you have another one at the C6 position. Other dihydropyridines actually have larger alkyl groups. And so larger alkyl groups are tolerated at those two positions here. All right. So if I was, for instance, to take, let's say we take amlodipine here. If we take amlodipine here, and which is number 1, 2 position, 3, 4, 5, 6. Okay, you see that this amlodipine molecule actually has a larger alkyl side chain here. Amlodipine still has the phenyl group at the 4 position, and then amlodipine has a chloro group here that is actually positioned meta at the meta position here. And so all these are actually going to enhance the activity of amlodipine. Again, when you look at this molecule, you see that at position 3 and 5, you actually have 2 different kind of esters, and so this will be an asymmetric compound. In addition to that, you also have different groups at 2 and 6 position. So this is an asymmetric compound, as we mentioned, and these compounds are usually have better affinity for certain types of blood vessels. Okay, so that's a good example. Let's take another example here. This is nifedipine. We've already mentioned nifedipine. Let's talk about felodipine for a minute. So felodipine, if we want to number it again, 1, 2, 3, 4, 5, and 6. Okay, so we're looking at some of the key structure activity relationships here. We said that the N1 position should not be substituted, and this is what we observe. We talked about compounds that are asymmetric, are more specific. The group here, this ester group here, is different than the ester group here. As you notice, you have an extra carbon here that is not present. So this is an asymmetric compound. It's an asymmetric compound. All right. Again, you have esters at position 3 and 5. So you have esters. That's good. Um, you have a phenyl group at position 4. Phenyl group at position 4. That phenyl group has substitutions both at the ortho and the meta position. All right, substitution at the ortho and the meta position. And so, as you look at the structure of all these dihydropyridines, you see that the structure-activity relationship that we have studied holds true for those dihydropyridines. Now, let's focus on the physical-chemical properties that affect the pharmacokinetic here. Now, all of the dihydropyridines have good lipid solubility and also excellent oral absorption. Now, they undergo a significant amount of first-pass metabolism, which is going to affect their bioavailability. Okay, they are marketed as a racemic mixture, and something to note is the fact that you have a nitrogen at the N1 position does not mean that that nitrogen is actually basic. So it is not a basic nitrogen. It is actually part of a conjugated carbamate. So it's not a basic nitrogen. Diltiazem and verapamil are both lipophilic. They are both asymmetric compounds, and they are used as racemic mixtures. And I hope you remember from organic chemistry, racemic mixtures, you can either be R or S. And so when you have two enantiomers, the R enantiomer and the S enantiomer together, not separated, you have a racemic mixture. Racemic mixture. And these are the structure of verapamil and diltiazem. So in order for you to have a racemic mixture, you need to have compounds that have mirror images that are not superimposable upon each other. Mirror images, not superimposable upon each other. And so you need to have compounds that have mirror images. For that to happen, you need to have stereocenters. The stereocenter is a carbon that has 4 different substituents. In this case, you have a cyano group here. You have an alkyl group here. You have the phenyl ring in this position, and then a different group here. So there's 4 different groups that gives you a stereocenter here, and that stereocenter can have either R or S configuration. When you have both of those compounds not separated but in a mixture, that's when you have a racemic mixture. The final point that we will mention about calcium channel blockers is the metabolism. Metabolism of calcium channel blockers. The main route of metabolism for the 1,4-dihydropyridine is oxidative metabolism to inactive pyridine. So it basically inactivates the drug through oxidative metabolism. Now it's not really obvious, so let me walk you through it. This is the 1,4-dihydropyridine ring here. Notice the presence of this hydrogen. There is a hydrogen here on this nitrogen. Now, because of the oxidative metabolism that takes place through the CYP3A4 enzyme, when you look at this pyridine ring here, there is no longer a hydrogen, but there is a double bond between the nitrogen and the carbon. Okay, so by this mechanism, by this oxidative mechanism, you are generating a pyridine ring that is inactive. So the hydrogen was removed, and then you have the formation of a double bond at the nitrogen. Now, so after oxidative metabolism happens to to form the inactive pyridine analog, then you can have additional transformations such as ester hydrolysis. So these esters that are at this position here, at the 3 and 5 position, these esters can actually be inactivated by esterases. All right, and it can happen after the oxidative metabolism. So the esterase will basically cleave at this position here, or it could happen before the oxidative metabolism, where the esterase is going to cleave and liberate an inactive metabolite here. All right. Now, this is an example with nifedipine here, where you have an inactive metabolite. Diltiazem also has quite a number of sites where metabolism can take place, and this still takes place through the CYP3A4 enzyme. So when the CYP3A4 attacks at this position, you have demethylation. You can also have O demethylation at this position, or hydrolysis. And the hydrolysis actually yields the primary metabolite, which is still 25 to 50% active. Now, verapamil's metabolism yields also a compound that is 20% as active as the original drug. So, it's just good for you to recognize that some of these metabolites are still going to be active. Okay. Now, diltiazem and verapamil, at the end of the metabolism process, by both CYP3A4 and CYP2D6 enzymes, diltiazem and verapamil are going to be completely inactivated. So these are steps in the metabolism process, but as you continue through the metabolism process, these compounds are going to be completely inactivated to lead to their excretion. Okay. I hope this lecture was useful. Hope it helps you review the material and get a better understanding of it. And thank you for taking the time to watch this video.